Imagine a world powered by energy that is virtually limitless, produces no carbon emissions, and leaves behind very little radioactive waste. This is not science fiction, it is the promise of nuclear fusion, often called the Holy Grail of clean energy. For decades, scientists around the globe have been working to harness this incredible power, the very process that fuels our sun. But now, this scientific endeavor has transformed into a high-stakes international competition, a race where one nation is pulling ahead, investing vast resources, and potentially changing the global energy landscape forever. That nation is China. Just a few years ago, where there was once open land, China has constructed a world-class fusion research campus. This facility is a testament to China's commitment, a stark contrast to the United States, which currently lacks anything comparable. This rapid development is a clear signal of China's increasing investment in nuclear fusion, a field many scientists believe holds the key to our energy future. If American companies do not lead in this area, then the jobs, the wealth, and the technological advancements will not develop in the United States, they will develop in China. What is truly at stake if China emerges victorious? To truly grasp the significance of this race, we must first understand what nuclear fusion is. Fusion has the potential to create nearly limitless energy with no carbon emissions and very limited radioactivity. The process involves combining two small atoms, such as hydrogen, to form a single, heavier atom. When this occurs, a huge amount of energy is released. To make these atoms collide and fuse, they are heated to an extremely high temperature, forming a plasma. Plasma is essentially a mix of positively and negatively charged particles, a state of matter often referred to as the fourth state of matter. Up until approximately 5 years ago, fusion was largely regarded as a long-term, fundamental scientific challenge. During that period, there was a great deal of open collaboration and discussion among scientists from around the world. George Tynan, a global fusion expert who has worked with several of China's top universities, as well as China's first nuclear fusion research institute, notes this shift. He observes that in the last 5 years or so, there has been a dawning realization that fusion may not just be interesting science, but there may be a possibility that this could become an important, practical technology. Tynan himself has not been back to Chinese labs since before 2020, partly because the United States government has discouraged such visits. The landscape of fusion research has changed dramatically, moving from pure scientific inquiry to a strategic national priority. Some scientists are now suggesting that fusion energy could be on the grid as early as the 2030s. China's journey to becoming a leader in this field began when it joined the International Nuclear Fusion Research and Engineering megaproject called ITER in 2003. Since then, China has invested heavily in domestic fusion infrastructure, research, and workforce development. This is not a haphazard effort, it is a deliberate and well-funded strategy. One of the leading candidates for a viable and practical fusion reactor is called a tokamak. This machine confines plasma using strong magnetic fields, creating the conditions necessary for fusion to occur. The United States currently operates 2 main government-funded tokamaks. China, on the other hand, has 3. Its 4th tokamak is expected to be completed in 2027, further extending its lead in infrastructure. The disparity in human capital is even more striking. China boasts 10 times as many PhDs in fusion science and engineering as the United States. Furthermore, the Chinese government has launched new fusion education programs across the country with an ambitious goal of training 1,000 new plasma physicists. This massive investment in human resources ensures a continuous pipeline of talent for their fusion ambitions. Beyond sheer numbers, the work ethic and operational capabilities in Chinese labs are notable. Researchers in China work very long hours. Some of the experiments in China can operate on a 24-hour, 7-day-a-week basis. Observers have seen them running multiple shifts, maximizing the use of their facilities. This relentless pace is partly enabled by their technology. Most Chinese tokamaks use superconducting magnetic coils, which have the advantage of being left on for days or even weeks at a time. In contrast, the United States has mostly been using copper magnets, which dissipate a lot of energy and need to be cooled down after being on for just a few seconds, limiting their operational time. The American fusion infrastructure in public facilities is quite old. They are honestly not of the leading edge. They do not compare with the things that China has. While the United States Department of Energy maintains that the DIID tokamak continues to be a world-leading device and an update to the NSTXU tokamak is almost complete, some United States scientists express concern. They point out that China has a habit of copying United States designs. For example, some United States scientists believe that the new tokamak China is building is a copy of one designed by Commonwealth Fusion Systems, the largest private fusion company in the United States. This is not an isolated incident. The East Tokamak, for instance, had its original idea generated in the United States in the 1990s. However, for a variety of budgetary reasons, the decision was made not to pursue that project. Then, in the early 2000s, China built that device with largely homegrown technology. China's Institute of Plasma Physics did not respond to requests for comment regarding these claims. The issue of intellectual property extends to the private sector as well. Helion Energy, a United States company, has accused Chinese companies, ENN and HHMAX, of copying its plans. One company launched a direct copycat program pursuing Helion's design, and another publicly stated its intent to replicate key aspects of Helion's approach. ENN and HHMAX did not respond to requests for comment on these accusations. China also appears to be following a commercialization program strikingly similar to the roadmap that hundreds of United States fusion scientists and engineers first published in 2020. The Department of Energy has really not built anything within this plan. The Chinese have basically implemented and built the test stands that will enable them to commercialize. The Department of Energy states it is building new facilities and that its fusion science and technology roadmap will be released next spring. It also claims the new plan is different from China's public sector-led approach, and the report will not contain all the details, making it difficult for China to copy it. However, there is a long history in China of being fast followers, of taking the knowledge learned and then investing it into domestic Chinese industry. This pattern has been observed in solar power, electric vehicles most recently, and in high-speed rail. The Chinese government is also spending double what the United States is spending on fusion research and development. In December 2023, the Chinese government launched a new state-owned company specifically designed to pull resources from across the country for fusion development. China's ambitious goal is to build the first industrial prototype fusion reactor by 2035 and to begin large-scale commercial production of fusion energy by 2050, according to a 2022 scientific report. In the United States, industry experts lament that the fusion budget has not been enough to keep up with inflation, hindering progress. Despite this, the United States has historically attracted far more private investment than China. Of all the fusion companies founded since 1992, over 50% are United States companies, while only 4% are Chinese. This is the key thing that the United States can leverage, the dynamism and innovation of its private sector. However, China's private sector is quickly catching up. Though United States industry experts often find it difficult to distinguish between private and public funding in China due to the nature of their economic system, the growth is undeniable. Energy Singularity, a startup in Shanghai, managed to build its own tokamak in just 2 years. The company states it expects to have a device that can feed power to the grid before 2035, mirroring China's national timeline. This rapid development in the private sector, even with potential government backing, indicates a powerful momentum. Even if the United States ultimately wins the race to achieve fusion, there is a critical concern about scaling up the technology. There simply is not enough capacity in the United States, or in like-minded countries, to support the real exponential growth that is expected to be seen. This highlights a significant challenge beyond just scientific breakthrough. One of China's inherent advantages lies in its existing dominance of manufacturing supply chains. Important manufactured goods like power electronics and capacitors, China has really cornered the market on. This manufacturing prowess means that even if another country develops fusion technology, they might still rely on China for critical components to build and deploy fusion reactors at scale. Furthermore, China is building more nuclear reactors than any other country. Some industry experts believe this extensive experience in nuclear construction would give China a significant advantage when commercial fusion is reached, allowing them to rapidly deploy the new technology. The implications of China winning this race extend far beyond energy independence. We should expect it to be a net loss to American global influence around the world. China will leverage this technology as something that they can support their Belt and Road allies with. Their customers will then need to buy from them and do business with them for the rest of the century, solidifying China's geopolitical standing and economic power. The ability to provide clean, limitless energy would be an unparalleled tool for international diplomacy and influence. United States fusion experts remain optimistic about the private sector's progress, acknowledging its vital role. However, they uniformly stress that the industry still needs substantial support from the government to truly win this race. They advocate for robust public-private partnerships. Commercial space exploration, for example, came about because NASA invested over $500 million in a public-private partnership that supported companies like SpaceX and Blue Origin. This is not an unprecedented approach, it is a proven model for fostering groundbreaking technological advancement. Fusion is a very hard problem to solve. It takes sustained effort, sustained over many, many years, even over decades. Maintaining that level of energy and effort will be the biggest challenge in the United States. The scientific hurdles are immense, the engineering complexities are daunting, and the financial investment required is colossal. This is not a sprint, it is a marathon that demands unwavering commitment and consistent funding. The race for nuclear fusion is more than just a scientific competition. It is a battle for future economic prosperity, global influence, and environmental sustainability. The nation that successfully harnesses fusion energy first will gain an immeasurable advantage, potentially reshaping the geopolitical landscape for generations. China's strategic, top-down approach, coupled with massive government funding and an expanding workforce, has positioned it as a formidable frontrunner. Its ability to rapidly build infrastructure, train experts, and potentially leverage existing manufacturing capabilities gives it a significant edge. The long hours worked by its scientists and the continuous operation of its advanced tokamaks underscore a national resolve to achieve this goal. In contrast, the United States, while possessing innovative private companies and brilliant scientists, faces challenges with aging public infrastructure and a more fragmented funding model. The reliance on private investment, while a strength in some areas, requires careful government support to ensure that the foundational research and large-scale infrastructure necessary for fusion are not neglected. The accusations of intellectual property infringement also highlight a complex aspect of this competition, where innovation and protection of ideas become crucial. The implications of this race are profound. A world powered by fusion energy would drastically reduce reliance on fossil fuels, mitigating climate change and improving air quality globally. Energy poverty could become a relic of the past, as affordable, abundant power becomes accessible to more people. However, if one nation monopolizes this technology, it could create new forms of dependency and power imbalances. The United States has a rich history of scientific innovation and technological leadership. To maintain this position in the fusion race, it must address the challenges of funding, infrastructure, and workforce development with renewed urgency and a cohesive national strategy. The lessons from past successes, such as the space race, demonstrate that focused public-private partnerships can deliver extraordinary results. The question is no longer if fusion energy is possible, but rather who will achieve it first and how its benefits will be shared with the world. The next few decades will be critical in determining the outcome of this monumental scientific and geopolitical competition. The stakes could not be higher, as the future of clean energy, global power dynamics, and environmental health hang in the balance. The world watches as China makes its bold play for the holy grail of clean energy, challenging the United States to accelerate its efforts and ensure a future where limitless, clean power benefits all.